Hi, and welcome to Jrockit, inside the Java virtual machine. I'm Nick Majorano, and I'm from Thoughtful Solutions. Okay, so let's get started. Our objective today is going to be to explore Jrockit's garbage collection. So this is going to be a fairly deep dive. We'll discuss Jrockit compaction, we'll understand configuration impacts on performance, and we'll interpret those cryptic Jrockit logs. So Jrockit is a JVM that was developed by Appeal Virtual Machines. It later got acquired by BEA in 2000, which incidentally got acquired by Oracle in 2008. It was bundled with WebLogic and continues to be bundled with WebLogic, and has been known to be faster than Hotspot for certain types of applications. It's of course compatible with Hotspot generated bytecode. Okay, so here's a pop quiz. So when do you think garbage collection was invented? Was it 1984, 1996, the year Java came out, or C, 1959? Well, the answer of course is 1959. So GC theory predates Java by over 3 decades. Jrockit is built upon decades of academic research, and it mixed and matched concepts, and in my opinion built a better mousetrap. So there are 2 axes of Jrockit garbage collection. These are garbage collection threading, so this relates to either parallel or concurrent. So when we say parallel, we mean that the cores of a CPU are parallelized to speed up the garbage collection process, versus the concept of concurrent, where garbage collection runs concurrently with your own application to minimize pause times. The second axis is heap segregation. This is when we split up the memory into generations or have a single spaced one. We'll talk about this in much detail. But to really understand, we first need to look at some garbage collection theory. So there are 2 types of garbage collection algorithms. These are copy and mark and sweep. Let's start by the copy collection algorithm, see how it works. So copy collection splits memory into 2. So we have the first region and the second region. There's only one half active at any one time. So the GC kicks in when it runs out of memory. And it starts from the root set, known as R in this case, and this is really the root to determine which objects in memory are active. In our case, only objects A, B, and C are reachable from the root set, so this is obviously very simplified memory, just for example. When garbage collection kicks in, the live objects are then moved over to the second memory. Pointers are updated because they're physically being changed. And the unreachable objects are of course treated as garbage, and these happen to be objects D, E, F, and G. Of course these are then reallocated and put back into the free list, so that their memory locations are available for new objects. Now the region number 2 is the active one. So now let's see how the mark and sweep works. So in this case we only have one memory region. We still identify the live objects from the root set, in this case again A, B, and C. The live objects are marked, and these are known to be the ones that are live. The unmarked object then are those that were not connected to any one of the live, and they're treated as garbage and reclaimed. So when we look at these 2 different types of garbage collection schemes, we have the copy, which is fast for small heaps, whereas in the mark and sweep can manage bigger small heaps. The copy really has a sweet spot where it works very well, but this unfortunately does not scale very well beyond that sweet spot, whereas this mark and sweep scales well. Copy is therefore best for small heaps, where mark and sweep is best for the big heaps. Okay, so now that we have some basic garbage collection theory, let's see how Jrockit implements these concepts. So Jrockit's answer to minimize GC pauses is concurrent mark and sweep. So we're taking concepts from GC academia and we're mixing and matching together to come up with a very viable strategy. So let's see how the concurrent mark and sweep works. So these are the actual steps from a high level of the actual collection, and we have on the left the garbage collection steps, and on the right we have run threads, which means that we're able to run the application so at the same time that this garbage collection is happening. So as you can see, some of the steps can be done at the same time that the application is running. So concurrent mark and sweep dedicates one core the entire time for collection. These parts here, concurrent marking, pre-cleaning, and these other two sweep steps, can actually be done concurrently with the app threads. These other steps do pause, but only when necessary, within those steps, of course. This makes app responsiveness. Now let's look at how the parallel collection works. This is Jrockit's other collection type. So this is slightly different. We have a separation of tasks. So the collection, the parallel collector, will separate the heap and assign certain steps, the mark and sweep, to as many cores as are available. So the collection here is parallelized, which means it's run in parallel and uses all the cores, as you can see, as many as there are available. Of course, this means that the threads are paused for the entire collection. So throughput is maximized, but obviously not responsiveness. When we compare the parallel versus concurrent, you see the parallel is actually faster, but concurrent has shorter pauses. Parallel is better for batch processing, whereas concurrent is better for app responsiveness. So obviously, as all other things, you have to choose based on your type of application. So what's the takeaway so far? Copy collection is best for small heaps. Mark and sweep is best for bigger heaps. Concurrent is best for the real-time apps. Now let's move on to this other important topic, which is heap segregation. So Jrockit separates the heap in two ways. The first way, which is of course configurable, is what we call the single-spaced heap segregation. So everything is created in this one space. There's no discrimination. So all objects are, regardless of their age and size, are created in this space. The heap is then marked and swept. That's the strategy that is used in this kind of heap segregation. The second way is to use generations. We have the nursery and the old generations. So new objects are created in the nursery here. Then live objects, whenever there is a garbage collection in the nursery, are promoted to the old during garbage collection. So promoted in this part of the heap. The nursery uses parallel garbage collection, whereas the old is mark and swept. So nursery uses copy garbage collection in a parallel way, and old is mark and swept. So obviously the nursery is collected first. If there's more space that is needed during a garbage collection, then a full GC is done on the old collection. Now, nursery garbage collections are short, and so the pause time will be minimized. So the generation uses a best of breed approach. Copy for nursery, again best for small heaps, and mark and sweep for the old. That scales better, right? So we're taking the best types of algorithms depending on the regions that we're talking about in the generation. So this is it's a very viable strategy for Java apps with many temp objects, which are of course which is in the case of object-oriented languages such as Java, which create many temporary objects. This works very well in that case. It also allows large heaps to be used, which is something that's very useful, of course. When we combine this together, we get 4 different types of Jrockit algorithms, and GenCon happens to be the best for high throughput servers. So it's a nice compromise between everything. So let's look at some tuning for high performance. So the nursery should be around 8 to 10% for total heap. So these are strategic numbers. If we go back to the garbage collection theory, we said that the copy collection worked for it has a sweet spot for small heaps. And this is why if we stick to these numbers, we get a small heap, generally speaking. The idea is also to use 75% of memory that is available on the hardware, and the remaining 25% is for the actual Jrockit overhead. Use GenCon as was previously suggested, and the Java min-max heap sizes should be equal so that there is no time spent in readjusting the size when you go over that number. And the target as well is to keep pause times under 500 milliseconds. So these are the actual Java command line parameters that you would use in this case. So you have the -x gc GenCon and the min and max plus the nursery size, which is the .ns, -xns. So you can also enable garbage collection verbosity with these parameters, and you will get something looking like this. So this applies for obviously the generational types, so it could be GenCon and GenPar. So what this means is that this is the line that tells you when the garbage collection started since the beginning of the Java virtual machine start. This tells you the heap size before the garbage collection and after, and the total size, and of course how much time was paused. Now this is the time that the application was paused, not necessarily the time that the garbage collection ran. That's the important. For the old collection, we have something that is similar. So again, we have the start time, the end time, the size of the heap before and after, total heap size that was allocated, and the sum of pauses again. Not the time of the garbage collection, but the actual pause time. Now let's talk about compaction. This is the last piece of the DDM puzzle, a very important piece, of course. So obviously over time, when you have Java applications that are running for days, weeks, and months, every time there's garbage collection that is triggered, this leaves many holes in the heap. Over time, you get objects that are scattered throughout the heap. And the result of all this is that you get dark matter. These are the spaces between the objects. This is similar to what you would have on a file system when you get fragmentation. Same idea, but applied to a heap. Now, dark matter is a bad thing because it causes heap fragmentation. Your free lists are fragmented. This is the list where new objects are allocated. And you get slower allocation because your free heap is scattered. You can't get contiguous blocks to allocate new objects. You get page faults for that, very bad things, and of course this leads to performance death. So compaction is something that kicks in and reorganizes the heap. It runs after every full garbage collection. And it keeps fragmentation under wraps. It keeps it under control, if it's well tuned, of course. Now the way Jrockit implements compaction is it divides the heap into what is known as parts. And it compacts one part for every garbage collection that is done. So the full and the old, obviously. This is what it might look like. We have two types of compaction. The internal type, which is something that is done within each part. So the idea here is to compact it within every part that you have. Whereas your internal compaction is to make sure that all the objects tend to stick to one part of the heap and they're not scattered everywhere. That's known as the external compaction. The goal of internal compaction, of course, is to keep all objects contiguous from the start of the part as tightly as possible. Make it easy to allocate new memory. In that case, memory is just allocated from the end of that block, or the end of the actual last object of that block, I should say. And it works from the start of the heap and goes on to the end. This is what it might look like when it compacts. Now, external compaction, the idea here is to keep all the empty parts at the end of the heap so that you have all the objects at the beginning of the heap, and this improves locality, so there's less page faults. And compaction, external compaction, works from the end of the heap and works its way backwards, which is, this is what it might look like. So see, as we've seen in this case, the last block here, block N, is completely empty right now, and it pushed everything onto the first part. So the way these will work is you'll have one cycle of internal compaction, one cycle of external compaction, and internal compaction will move from one up higher to the heap, whereas external compaction will start from the end and work its way backwards, then it will meet to the middle and then start over again. So now, whenever you increase the number of parts, you get finer grained parts, obviously, because each part is smaller. You also get increased part density. You get reduced dark matter, faster allocation because of closer locality, but increased pause times, and you have to be careful because that could create heap lumps, whereas you have a lot of objects in a part, and that makes the garbage collection work harder whenever it has to compact that. So increased part density, reduced dark matter, and faster allocation is obviously a good thing, whereas increased pause times and lumps are a bad thing. Whenever you decrease the number of heap parts, you get coarser grained parts because each part is bigger. You get reduced pause times and increased dark matter and reduced part density. So you get slower allocation because it's further locality. Needless to say, reduced pause times, that's a good thing, whereas these other three are a bad thing. Okay, so now when it comes to compaction recommendations, the idea is to aim for about 10% dark matter into your heap. Now, of course, ideally we don't want to have 0% dark matter, but that's just not an attainable goal, whereas 10% is actually attainable and will give you fairly decent performance. So 10% is really just the overhead and the cost of doing business. The heap parts should be sized at around 15 megs each. And compaction pauses should never account for more than 100 milliseconds. You also want to avoid object lumps. This is when there's too much density in every part, which will really slow down the compaction part for future compactions of that part. Mission control is always a good idea to use to view the dark matter. Now, when you actually configure this compaction, you could use the heap part option and say that you have 1 gig of memory, and you would say that you have 1024 parts. That would mean that each part is 1 gig, for example. Just use a round number. To determine how many parts are compacted per cycle, this can actually be specified with these two flags, so the internal compact ratio and the external compact ratio. And if we say 1 for each value, that means that every full cycle, every garbage collection cycle in the old, there'd be 1 heap part that would be compacted, either external or internal. You can also limit your density by setting the amount of objects there should be in every part. So that's the idea is how much should I compact, and never go beyond that. If you want to enable verbosity for compaction specifically, you can use this flag, the verbose compaction flag. You'll get something like this, which is very cryptic and really doesn't have any documentation, but I'll tell you what this is. So every time you get a full cycle, full garbage collection cycle, you'll have one line that prints out like this in your log. And here's what these mean. So 1 would be the cycle count, so this is just a number that's going to increase throughout the life of your application. This is the number, the part that is being compacted at this time. So it will go from this example from 4091 to 4086. So we can see this is an external compaction that's working its way backwards. In this case here, the JVM has been configured to compact 5 parts per cycle, and as I said, 2 is an external. we have these flags here, which mean is this an emergency compaction or not. In this case, it's 0. This is the actual time spent compacting. And we have the limit, which is in this case here 50. The amount of time that was spent updating the references, the limit that we have for that, and the number of references in this part, which is there are 57,000 objects in this case, and we configured the JVM to have 1 million max. So that means that basically we want to update as much as possible. So now remember, final words: there are no slow Java virtual machines. There's only mistuned ones. So I hope you've enjoyed this. Thank you very much for your time.